last section of chapter 2 is section 2.4, sums and direct sums of subspaces. So we start with the definition. Let U1, Un be subspaces of V. The sum U1 plus U2 plus all the way to Um is defined to be the set. The notation, first of all, is the summation notation with sigma. I goes from 1 to M, U sub I, and it's defined as the set of vectors U1 plus U2 plus all the way to Um, where these vectors Ui are from the subspace Ui for I going from 1 to all the way to M. So this is the definition of a sum of subspaces. Next definition, this is about the independence, and it will be about an ordered list. So we have these subspaces U1, Um, and we call this a set to be independent if U1 plus Um equals to the zero vector with all these Ui's vectors from the Ui subspaces, I going from 1 to all the way to M, can occur only if all these Ui vectors are actually the zero vectors for all I going from 1 to up to M. So this is really similar to the undergraduate concept of independence of list of vectors, but here instead of just vectors we have whole subspaces, and we define the independence of list of subspaces. So we will have the first theorem in this section, theorem 2.4.1, that says that let U1, Um be subspaces of V. Then we have that the list U1, Um is independent if and only if, so this is a equivalence statement, if and only if each element V from the sum vector space or sum of the subspaces has a unique representation of the form V vector equals to the sum of Ui vectors, I going from 1 to M, with some Ui from the Ui subspace as I goes from 1 to through M. Let's prove this theorem. So we already had the definition of independence. This is one thing that we have to consider, and it's supposed to be equivalent, the independence of this list, with the unique representation of vectors. The representation itself, the existence of the representation is not in question, since the definition of the sum of Ui's is that is the sum of all vectors. So if a vector V is in the sum, that means it does have this kind of representation. The question is really the uniqueness, whether it's unique or not. So we have to prove in both directions these implications for the equivalence. Let's start with this direction. That means that we suppose that the list U1 is independent. By the definition of independence, well, if you look at the definition, it actually says that 0 can be represented only one way, with all zeros sums. So at least the 0 has unique representation according to the definition. Let me write this down. By definition of the independence, 0 has a unique representation, and that's 0 plus all zeros from the different subspaces ui must be added together, and that's how we can get the 0. Yeah, so the first 0 is supposed to be from u1, and the last 0 is supposed to be from All right, so we know that according to the definition of independence. Suppose that some v in the sum has two representations. Let's write this as v equals to the sum of, say, ui's, and that equals to the sum of, say, vi's, with the ui vector and vi vector together both from ui for each I equals to 1 through m. So we look at this part of the as an equation, and we rearrange this to obtain. We rearrange it to one side, say to the right hand side, so we get 0 equals the sum of vi's, I going from 1 to m, minus the sum of ui's. Again, well, we write minus as plus with minus with the additive inverse of ui's. That would be the original way to write it. But then we understand that subtracting means adding the negative. And then we collect index by index these terms. So we will have vi minus ui. And then since ui is a subspace, the difference of these two vectors, again, let me write this, that this is really the sum of two vectors, vi and minus ui. So both of these are from ui, and then that means the sum is also from ui. So what we get here, that this is a representation of the 0 vector, but this is supposed to be unique. So that means that vi minus ui must be equal to 0, and that means that vi equals to ui for all I. So we started with two possible representations, sum of ui vectors, sum of vi vectors, and then it turned out that this is really not two different ones, because all these vectors are the same, which exactly means that the representation is unique. That was the end of one direction, showing that the representation of all vectors is unique if the list is independent. Let's continue now with the other direction. If every element has unique representation, then that means 0 also has. And it already definitely has one representation when you add a 0, and that means that this is also unique, which is exactly what the definition of the independence, that the only way to get the 0 vector is if all the entries in the sum are zeros. So this finishes the proof of the whole theorem then. Next definition. So we consider this case when each element of in the sum of these subspaces has a unique representation in the sum. Then we call the sum a direct sum of subspaces, direct sum of subspaces, and we write the sum I going from 1 to m of UI subspaces, instead of the regular plus sign, we will use this circled plus sign for the direct sum. And if we want to use the sigma notation, then what we do is we write this circled plus in front of the sigma notation. So as before, we show examples, starting with possibly the simplest example, R2, the Euclidean coordinate system, two-dimensional. So there we have points x, y, or vectors pointing from the origin to point x, y. And then we already have that subspaces could be any line going through the origin. But now we consider special subspaces. Let U1 be the subspace x0 vectors with x in R. So this is actually the x-axis. And it's a straight line going through the origin. And then U2, let's consider this to be the 0y vectors, where y is any real number, or it goes through all the real numbers. And this is the y-axis, which is again a straight line going through the origin. If you have xy, let me write it in a column format, the xy vector in V, which is R2, then this xy vector could be uniquely written as x0 plus 0y. So that means that this is in the direct sum of U1 and U2. So this is actually another proof that this can be written uniquely. I just mentioned that we can write it uniquely. If you wanted to use the theorem about the equivalency of unique representation and independence of the list of subspaces, then it's actually easier to show in this case that the U1, U2 list is independent. For this, we have to show the uniqueness of the representation of the 0 vector. So if we have x0 plus 0y using this U1, U2 representation, then this can happen if and only if x equals to y equals to 0, since the way we add together vectors is that this will be the xy vector. And comparing the xy vector to 0, 0 vector, we have that actually both of these vectors must be the 0 vector. So this 0 has a unique representation. That means U1, U2 is independent, and that means that U1 plus U2 is actually a direct sum. So all the representations are unique for all vectors. Another theorem about direct sums, theorem 2.4.2, let U1, Um be subspaces of V such that, so the new thing here that we're going to consider is that we not just consider the sum of the subspaces, but a special case when actually the sum gives up all the whole vector space. Then the following are equivalent. One, that V is actually a direct sum, which means it has unique representation. And then the second, that's equivalent to the first. It's a little bit strange, so we're going to have to look at what it really means. It says that U sub j subspace intersected with the sum of U sub I, where I goes from 1 to m, but we exclude j from this. So that means uj's intersection with the sum of all the others intersected with the sum of all the others. So this intersection is supposed to be not the empty set, but the set with only the zero vector. And this is supposed to be true for each j, going from 1, 2, all the way to m. So a proof of this theorem, we have to show that 1 is equivalent to 2. Again, it has two directions. First, we show that 1 implies 2. Suppose 1, which means v equals to the direct sum of u sub I subspaces. Let's take any u vector from u sub j intersection of this sum of the rest of the subspaces. So I going from 1 to m with I not equal to j. So we take a vector, it's in the intersection, that means it's in both. So since this is u is in j subspace, that means that u equals to uj for some uj vector from uj subspace. But then it's also in the other sum. So since u is in the sum of the ui subspaces as I goes from 1 to m and I is different from j, that implies that u can be written as a sum of some vectors from these ui subspaces as I goes from 1 to m and I is different from j with some ui in ui, I going from 1 to m. And again, I is not equal to j. We set these two expressions equal to each other. U is u sub j vector, and also it's a sum of some other vectors. That kind of already tells you that they seems to be two different representation. But the way we show that this can only happen if u is 0 is that first of all, we write down that u equals to uj, and then this equals to u1 plus u2 all the way up to uj minus 1, because we skip uj, so in the sum we don't have the uj. That means after u sub j minus 1, we're supposed to have u sub j plus 1, and then we continue all the way up to u sub m vectors. Take this equation and we rearrange it. We add the additive inverse of u sub j, simple algebra basically. So we get that we have u1 here, u2 all the way to uj minus 1 vector, j minus 1 vector. And then since this is in the uj subspace, we insert here this minus uj, taking it to the other side, and the rest of the sum. And then we have each of these are from the corresponding u space, and this is, for example, from the u sub j subspace. This is from u1 subspace, and this is from um subspace. We started with a direct sum. Assume that we have a direct sum. That means that in this representation, or all vectors have unique representations. That's the definition of the direct sum, including 0. And the unique representation is 0 plus 0 all the way. But then that means that all these u1s, u2s are zeros, 0 vectors, including minus uj also. And then if minus uj is the 0 vector, then we have that uj is also the 0 vector. And that means that the original vector we started with, that was u vector, notation. So with this we obtain that and u equals to uj equals to the 0 vector for all u vector which is from the intersection of uj with the sum of the rest of ui's. So if we have that, we take any vector, that's what we did here. We took any vector u from the intersection. It turns out that this is then the 0 vector. That means all vectors are 0 vectors in this intersection. So that means this whole intersection is just the set with the 0 vector. We didn't specify what j is, so that means this is also holds for all j in general. So this shows one direction, that 1 implies 2. The other direction, to show that 2 implies 1, if uj intersection with the rest of ui's, sum going from 1 through m, with I different from j, if this intersection is the set with the 0 vector only, and if we have a representation of the 0 vector with some u1, uj minus 1, actually let me just write here the j1 right now, and um vector. So let's say that the 0 vector can be written in this form with this representation. Then we rearrange this. Then let's rearrange similarly to what we did before, that we take this uj to the other side by adding the additive inverse to both sides, so that it disappears from the right hand side, and on the left hand side we get minus uj equals to u1 plus all the way up to uj minus 1. Then the next one is uj plus 1, since uj is missing, and then we continue all the way up to um vector. So then what we get here is that uj is in the uj subspace, then minus 1, it's a subspace, so when you multiply by minus 1, this is also in the uj subspace. And then this is in the sum of the subspaces ui from 1 to m by skipping the jth one. So I is different from j. So if we have this in both spaces, because they are equal, that means this is here and it's also in the other one. That means this is in the intersection, but the intersection is 0. That was the assumption, the 0 vector. So then this implies that minus uj is the 0 vector, and also the uj is the 0 vector. Doing this for all j, what we get is that uj equals to 0 vector for all j going from 1 to m. That means this representation of the 0 vector is unique. And that means that list u1 all the way to um is independent, and the sum is direct sum. The sum of ui's is a direct sum. So this finishes the proof, both directions. Let's see an example how we can use this. Again, we only consider m equals to 2, so that means we have R2 that we saw before as a direct sum of two subspaces. Now the difference will be, instead of this x-axis and y-axis line representation, so we considered this before, the direct sum of the x-axis and y-axis. So now we do a little twist on this. What we do now is that we consider, so this is a new case. So now we consider two straight lines, u1 and u2 that are not the x or y axis. They go through the origin. They are different from each other. So in this case, u1, u2 are subspaces. We looked at this before. u1 intersection with u2 equals to 0 vector. Their only intersection is the origin. And we have that then u1 plus u2, the sum is really the same as the direct sum. Maybe what's not clear that the sum itself equals to R2. Is it really the case? Well, we do have that if you have these two lines, we do have that if you have any xy point or xy vector, then from undergraduate linear algebra, perhaps, that we can draw lines parallel to this point, lines parallel to these other lines. And then wherever they intersect the u1, u2 lines, we get two vectors. And using the parallelogram rule, we get a representation. So we get some kind of u1 vector and u2 vector, such that this xy vector can be written as u1 plus u2. So using this parallelogram technique, we know that u1 plus u2 equals to the R2. The extra thing that actually we know now is that this representation is unique because the sum is actually the direct sum. So the representation is unique.